In today's lesson, we're going to discuss nuclear reactions and also radiation damage. Nuclear reactions occur when two nuclei come together, undergo some reaction, and produce other nuclei. These interactions between nuclei always conserve mass number. So if you add up the total number of neutrons plus protons in the reactants, then that will equal the number of protons plus neutrons in the products. So mass number, the total mass number, is conserved. The atomic number, which is the number of protons, is also conserved unless a positron or electron is produced by the reaction. Even if that is the case, the charge is always conserved. So if you consider the protons to be positive charges, and a positron as well, and the electron to be a negative charge, then if you add up all of those fundamental units of charge, the products will have the same charge as the reactants. Some nuclear reactions require the pre-reaction components to have kinetic energy. Other reactions produce products that have kinetic energy. It all depends on how mass is, the mass of the products compares with the mass of the reactants. So if you have a reaction where the mass decreases, so the Q value captures the amount of energy that is either consumed or produced by the reaction, and the Q value is equal to the negative of the change in mass times c squared. So if the mass decreases, that means mass is being converted from mass into energy. And so if the mass decreases, then kinetic energy is created, and the products will go flying off with a large amount of kinetic energy. In this case, the Q value is positive. This is an exothermic reaction. It's one that produces energy. The energy comes from the mass that went away. On the other hand, if the mass increases, there needs to be energy that you're turning into that mass. And so the kinetic energy is consumed and Q is negative. This kind of reaction is called endothermic, and it requires that the components that come together to form the reaction have kinetic energy to begin with, so that that kinetic energy is available to be turned into mass. So if we consider this reaction where we have a hydrogen, a deuterium actually, plus a nitrogen, and they combine and then produce carbon and helium, if we look up the masses of these atoms in the one table in the textbook, in the appendix, we can add up the masses and find that the initial masses of these two put together is this value here, the 16.017176 atomic mass units. And then if we add up the products, we find that they will have a slightly different mass. If we take the final mass minus the initial mass, we see we get a negative result. So mass is lost by this reaction. So since mass is lost, then there is a positive Q value. Some of the mass is turning into energy, and this would be an exothermic reaction. Here's another example of a possible nuclear reaction. Here we have a helium nuclei and a nitrogen, and they react, they collide with each other, and then they produce an oxygen and a hydrogen. Once again, we can add together the masses of the reactants and the masses of the products, and we find that mass is gained in this reaction. So what we end up with has more mass than what we started out with. So because of this, the Q value is actually negative, and we have kinetic energy turning into mass. So the kinetic energy of those pre-collision components has to be greater than the mc squared, the mass that's gained, times c squared. So at least some of the kinetic energy is used up in creating the mass of the products. So once again, if Q is negative, that means we have an endothermic reaction. You have to put energy in for the reaction to proceed. If Q is positive, then this is an exothermic reaction. It's one that produces energy. So just to sum up, we know that in a nuclear reaction, the atomic number, and the charge has to be conserved. So the total number of protons plus neutrons is conserved, and also the charge is conserved in a reaction. We can calculate the Q values based on the change of mass, and if we find a Q value that's positive, this is an exothermic reaction that produces energy. If it's negative, then that's an endothermic reaction that consumes energy. So if we have an endothermic reaction, one that requires an energy input so that some of the energy gets turned into mass, then one of the ways of doing that is by taking a lighter nucleus and throwing it against a target nucleus. So you have a very high kinetic energy incoming nucleus and a stationary target nucleus. In this particular instance, if this is your methodology for creating this endothermic reaction, then the minimum kinetic energy that the incoming nucleus would need is going to be equal to 1 plus the ratio of the masses times the absolute value of the Q value for the reaction that needs to occur. So here is a question for you. If the Q value of an endothermic reaction is 2.17 MeVs, then the minimum kinetic energy needed in the reactant nuclei, if the reaction is to occur, must be greater than 2.17 MeVs, less than, or exactly half of 2.17 MeVs.